The next topic we're taking a look at is curvature, and this is defined for smooth curves. So let's suppose that we have a smooth curve, and maybe it looks something like so. Of course, if it's smooth, it's oriented. Okay. So I want to imagine that this is a windy mountain road, and unfortunately, I'm one of those people who doesn't do well when driving along a windy mountain road. So it's much better if I'm driving, otherwise there is some danger that I'm going to get car sick. If you share this problem, it's actually going to help you in understanding curvature. This is a windy mountain road. Where are you most likely to get sick? That would be where the curvature is greatest. So here, this is a nice wide curve, but these tighter curves in here, that's bigger curvature. That's where you're probably going to start feeling that curvature more. However, there are things that you can do. So if you slow down and you drive really slowly around these very, very tight curves, you're not going to feel them so much. On the other hand, if you drive really quickly around even a wide curve, it can feel a lot more severe than it is. So that's a situation where the parameterization of our curve, which has to do with the speed with which we're drawing that curve, if it were a position function, it would be the speed with which we're moving around that curve, can affect our experience of the curvature. So mathematically, if I want to be able to talk about this and say, hey, the curvature is greater here at these very tight curves than it is here, I want to make sure that the parameterization, the speed with which we're drawing the curve, doesn't affect things. So for that reason, we're going to use the arc length parameterization when we're defining curvature. Okay. So if I've parameterized this curve in terms of the arc length parameter, which I can always do if it's a smooth curve, okay, then I know that r prime of s is actually the same as t of s. Ordinarily, to get to the unit tangent vector, I have to normalize the derivative. But remember, the magnitude of the first derivative is the speed with which we're drawing the curve. It's the rate of change of arc length with respect to the parameter. Well, if the parameter is arc length, it's the rate of change of arc length with respect to arc length. That's 1. So this is always a unit vector. Okay. The magnitude of r prime of s is always going to be 1. That was the whole point of coming up with the arc length parameterization, to make it so that we were drawing the curve at a constant rate, and more specifically a constant rate of 1 unit for every 1 unit of change in the parameter, and that means that the derivative is always a unit vector. Okay. So r prime of s and t of s are always the same thing. Now, what that means is if I take a look at the derivative of that, if I take a look at r double prime of s, which would just be t prime of s. Again, those are the same thing because the derivative is always a unit vector. This is looking at how t is changing. But if t was the unit tangent vector, then any change in t is just a change in direction. It's not a change in its magnitude. That's very different than if I look at the parameter, a parameter t, like time. The first derivative would have magnitude and direction, and the second derivative would be measuring how both that magnitude and that direction are changing. With an arc length parameterization, the first derivative does have a magnitude, but it's constant at 1, so that it's the unit tangent vector and the magnitude isn't changing. So when I measure the rate of change of r prime of s, or equivalently of t of s, it's just a change in direction. Okay. So we're going to define that kappa of s, that's a Greek letter kappa, looks kind of like a curvy K. That's going to be our curvature. We're going to define that to be the magnitude of the second derivative of r with respect to s, or equivalently, the magnitude of the unit tangent vector with respect to s. Again, those are exactly the same thing. Okay. Now, that's how we're defining curvature. At first glance, that does make some sense to me, because I'm used to second derivatives telling me something about the way a curve is curving. For real valued functions, we define that as the concavity of things. Now that we're talking about vector functions, we no longer have to pass, we no longer have to pass the vertical line test because we're not drawing the t-axis. So it's still a function. Each input, each t value has a unique r of t value associated with it, but a vertical line is not picking out all points that have a value of t. So now I can almost have like concave left and concave right and stuff like that. So we no longer talk about concavity, but we talk about curvature. And it does make some sense that the second derivative is going to tell us about that. What I'd like to do is, this is a definition, so you can't prove a definition, but you can understand a definition, and we can decide whether we think this is a good definition or not. There are a couple of things that I think any good definition of curvature should have. I think the curvature of a line should be 0. So if this definition tells me that a line has non-zero curvature, I'm going to be a little bit skeptical. And I also think that a circle should have constant curvature because it's always curving at the same rate. So let's go ahead and check that out. Let's take a line. So let's just say I have r of t equals r naught plus t times v. Now we looked at how to get to the arc length parameterization for lines, and it was actually quite simple. All we need to do is normalize the direction vector. So r of s would be r naught plus s times v hat. Fabulous. So now I just need to take the second derivative. Well, r prime of s, that's a constant, so its derivative is 0. This is a constant vector times my parameter. I just get v hat. Remember, the derivative of a line is the direction vector for that line. Okay, we worked that out component-wise a few videos back. If you've forgotten that, give yourself an example, write it out component-wise, convince yourself that it's true. But it makes sense conceptually that the derivative of a line should be the direction vector of the line. Okay, so then r double prime of s, and by the way, just to remind us, this is the same as the unit tangent vector. To be hat, it's a unit vector. Works out, great. So r double prime of s, well, that's constant. The derivative of a constant is 0. The magnitude of r double prime of s is therefore 0, the number. Notice curvature is a number, okay? And it's always going to be a non-negative number because it's a magnitude. So there's no such thing as having negative curvature. What we're going to see is that the bigger the number is, the bigger the curvature is. Okay, so curvature of a line is 0. Fabulous, that makes some sense to me. Let's take a look at a circle. Okay. Now if I start with r of t equals a cosine t, a sine t. So a greater than 0 is the radius of my circle. So I put my circle so that it's centered at the origin, and I've chosen to orient it counterclockwise. Okay, now we went through previously finding an arc length parameterization for this circle. R of s was simply a cosine of s over a, comma, a sine of s over a. That was a previous result when we were looking at curvature. You don't need to have that memorized, but it's kind of nice to know. It's a pretty simple one, but it's also a pretty quick derivation. Okay, so I'm just referring back to something that we previously demonstrated. Okay. So let's find r prime of s, which again, just to remind us, that's the same because it's arc length. That's the same as the unit tangent vector. R prime of t is not the same as the unit tangent vector. I would have to normalize that. Okay, so let's see. We're going to get a copies of negative sign s over a, chain rule, times the derivative of s over a, which is just 1 over a. Notice those a's now are going to cancel. Here we're getting a cosine of s over a. Chain rule gives us a factor of 1 over a, and those a's cancel. And so we're getting negative sine s over a, comma, cosine s over a. And I can recognize that's a unit vector because it has cosine, and the sign happens to be negative, but when I calculate the magnitude, I'm just going to get sine squared plus cosine squared of s over a. That's going to be 1. Okay. All right, so let's calculate r double prime of s. So that's going to be negative cosine of s over a, chain rule, times a 1 over a, comma, negative sine s over a, chain rule, times a 1 over a, which I'm just writing at the front. Okay. All right. So if I wanted to calculate the magnitude of that, I'm actually going to just rewrite that. That's r double prime of s is 1 over a copies of negative cosine s over a, negative sine s over a. So the magnitude of r double prime will just be the absolute value of 1 over a times the magnitude of this vector, but that's a unit vector because that's going to give me cosine squared s over a plus sine squared s over a. Now, because a was positive, because it was our radius, I can say that's just 1 over a times 1. That's 1 over a. So we did get that it's constant because that doesn't have any s's in it. So it's not, this is what I get at this s value and I get that at a different s value. No matter where we are on the circle, the radius is, or the curvature is 1 over a, or 1 over the radius. Okay. Interesting thing to point out, which of these circles has the bigger curvature? Okay. Now, you do need to be careful because I just drew 2 circles and then I used the word big. Obviously, that's the bigger circle. That has the bigger radius. This has the bigger curvature because the curvature is the reciprocal of the radius. And again, if we think in terms of just driving in a car and when we're going to get sick, if I'm driving in a car at a constant speed around this circle, and I'm driving in a car at the same speed around this circle, I'm getting dizzy, I'm feeling a little queasy here a lot sooner than I am here. So the relationship is that the curvature is the reciprocal of the radius. Bigger circles curve less. Smaller circles, it's a much tighter curve, they're going to have a bigger curvature. Now again, this doesn't prove our definition because you can't prove a definition. A definition is just somebody said this is what this word means. So that's what curvature means. But just looking at a couple of examples, we can say, yeah, that seems like a very reasonable definition. It does seem to be capturing what I feel like should be captured when we're talking about curvature.